Hey everybody, welcome back to another video. So in today's video, we are going to start renal physiology. And in this video specifically, we'll be talking about kidneys function, a little bit on its basic anatomy. We'll be talking about the glomerular filtration rate and the autoregulation of blood flow that the kidney does. So if you guys like the video, if you enjoy it, if it truly helps you, please consider subscribing, leaving a like, and maybe a comment. And let's get started. So the kidney has five main functions, okay? Five main functions. The first one is going to involve, of course, fluid and ion homeostasis. Okay, fluid and ion homeostasis. And by this, I really mean that it maintains the pH of your body. It maintains the ion balance. It maintains extracellular fluid volume, so fluid within the plasma, fluid within the interstitial fluid, right? It maintains that properly. And it also maintains your osmolarity, right? And you guys know that osmolarity is the number of solutes per kilogram of solvent. The next thing it does is it's involved in metabolic waste excretion. Okay, so metabolic waste excretion, and there's a couple of examples of this. For example, when you take the amino acid glutamine and turn, you can actually turn it into urea inside of the liver, and then that urea will be excreted out inside of the kidneys. Okay, and really you're turning this glutamine into urea because we're getting rid of this toxic metabolite called ammonia. All right, so that's one thing. And of course, there's other things, for example, like creatinine. Creatinine is a metabolic byproduct of the muscle's creatine. There's, for example, bilirubin, biliverdin, perhaps, many other things, okay? These are all metabolic waste products that will be excreted out in the kidneys. The other thing is drug removal, okay? Drug removal. And the next thing would be hormone production. Man, is the kidney involved in quite a bit of hormone production, actually. So it produces this hormone called EPO, right, erythropoietin, which actually stimulates the bone marrow to go through red blood cell synthesis. The other thing it makes is a enzyme called renin, so a hormone-like enzyme called renin, and renin is involved in the activation and production of angiotensin 2, okay? And you guys know from previous videos that angiotensin 2 does many functions, one of them being, for example, being a vasoconstrictor. The other thing is that it helps activate vitamin D, and you guys know vitamin D is a hormone, and it actually helps activate vitamin D through a specific enzyme inside of the liver called 21 alpha hydroxylase. But you don't have to know that. That's just how it works. The other thing it does is it contributes to the process of gluconeogenesis, or basically synthesizing glucose from non-carbohydrate sources. And technically, the kidney doesn't contribute much to gluconeogenesis. That is the function of the liver mostly. But there's data suggesting that more than a 12-hour fast, the kidneys are responsible for 25% of glucose production, and for a prolonged starvation period, the kidneys can actually go up to 40% of glucose production. So there's perhaps a role there. Now, just to give a brief kind of anatomy of the kidney, all right, we got to talk about something here. So the kidney's blood flow involves the renal artery. Let's zoom in here. Here's the renal artery, and then the renal vein, which then drains everything. Okay, and you can see they're both coming in here through this pilus region. Now, the other thing is this big guy right here. This big guy right here is actually called the renal pyramid. So this is the renal pyramid, and this dude right here is the renal pelvis. Renal pelvis. And this guy right here is technically the ureter. If you want, I can write this here. Here's the ureter. Okay. Now, the path of urine is actually going to be from this region here, the renal pyramid, all the way into these little minor and major calyces, and then it drains to this renal pelvis, and then to the ureter and so on. But before any of that even begins, we got to zoom in on this renal pyramid for a second. This renal pyramid contains the smallest functional unit of the kidney, okay? And you'll notice that there is two regions. There's this one light region, which is called the cortex, okay, of the kidney. And then there's this darkish striated region, which is called the medulla, okay? And what we're going to do is we're going to zoom in on this, and we're going to see what the functional unit kind of looks like. So here it is. Here's the zoomed in version. You're going to see a nephron, but this is a very complicated view. So let me break it down for you in a smaller view down here for a second, and then we'll go back there. So this right here, guys, is a nephron, okay? It's a nephron. You got about 1.2 million of these bad boys per kidney, all right? So in total, you got about 2.4 mil. That's a lot. That's a lot of these guys. Now, here is the general structure of a nephron. So you're going to have this arteriole feeding into this area, okay? So here's this nephron. Here's a nephron, right? This entire thing is a nephron. You have this arteriole here called the afferent arteriole, and you have this other arteriole called the efferent arteriole. You have this big tuft of capillaries here in red called a glomerulus, okay? So this guy is called the glomerulus, and let's change font size. All right, the glomerulus. You have this little greenish capsule surrounding this tuft of capillaries that's called the glomerulus, and that capsule is called the Bowman's capsule. It's made up of a whole bunch of epithelial cells. Okay, Bowman's capsule. And together, the glomerulus and the Bowman's capsule are called the renal corpuscle. Okay, the renal corpuscle. Now, this is a weird scenario. The afferent arteriole is bringing in arterial blood into this capillary right here, the glomerulus. Okay, the glomerulus is just a whole bunch of capillaries together. And the efferent arteriole is draining this capillary, the glomerulus, and is turning into this secondary capillary called the peritubular capillaries. Okay, we'll see it written in another image in a second. Now, when we continue off of this Bowman's capsule, right, there's going to be other things. So what's going to happen here? In this region of the glomerulus, right, we're going to bring arterial blood and plasma, and we're going to filter a specific amount of it into this Bowman's capsule. That's called glomerular filtration. So we're going to filter a specific amount of plasma into this Bowman's capsule. After we do that, the fluid will then continue to enter through these series of tubules. That is this nephron, okay? This is just a whole bunch of tubules made up of epithelial cells, okay? We'll take a deeper look at that in a second, but trust me on this. Now, once we move on, we have this other region called the proximal convoluted tubule. Convoluted just refers to the fact that it's all like bendy in shape, okay? It's super convoluted. And in this region, you might have some tubular reabsorption and some tubular secretion occurring. Tubular secretion just refers to this peritubular capillary, right, that runs quite pretty much adjacent to this convoluted tubule. It will have the opportunity to secrete certain molecules from this blood into the tubule for waste excretion. And any fluid that we filtered here in the Bowman's capsule that made its way all the way to the proximal convoluted tubule will have the opportunity to get reabsorbed back into the peritubular capillaries to escape filtration by the urinary system. So that's what tubular reabsorption and tubular secretion are. Now, if we follow down this proximal convoluted tubule, we'll run into another structure here in purple, and that is called the proximal straight tubule. Following that is this little thin portion called the thin, or actually I should write it like this. It's called the descending, thin loop of Henle. Okay, so it's descending, going downwards, and it's very thin, right? And it's a part of a loop, and this loop is called the loop of Henle, right? But this is the descending thin loop portion. This portion is the ascending loop. So here's the ascending thin loop. I'm just going to abbreviate it as LH, loop of Henle. And then right above that is the ascending thick loop of Henle. Okay, thick loop of Henle. And right above this, you can see we go back to this convoluted shape, but we're no longer at the proximal portion, the start portion. We're actually at the end, the distal portion. So they call this the distal convoluted tubule. The distal convoluted tubule. And this distal convoluted tubule connects to a specialized structure called the collecting duct. And this right here is where all of that filtrate, the filtrate, right? All the stuff that we filtered over here, right? That was flowing, making its way all the way to this collecting duct. That's where all of that will dump in. And at that point, when it joins this collecting duct, it is now called urine. Now, this collecting duct has two portions. It has the cortical region and the medullary region. And you'll see what I mean in a second here. Okay? But it has two portions, the cortical region and the medullary region. Now, all of this nephron, all of it, can be found literally from here all the way to there. Okay? So one nephron can be found all the way from here to here, or it can be found from like here to here. Okay? So that's that. That's why we are going to zoom in to this renal pyramid, which involves the actual medulla and the cortex. So let's zoom in. And here it is. Here's the zoomed in portion. And what you're going to notice is that the lighter portion, like I said, is called the cortex, right? The renal cortex. And the darker striated portion is called the renal medulla. The striations are really just due to the presence of these structures down here. Now, this was just one nephron. We actually have different types of nephrons. We have two types. We have what's called the cortical nephron, and we have another one called the juxtamedullary nephron. Okay? Now, cortical nephron refers to the location of it, and you can see that the majority of this nephron right here, right? So here's one cortical nephron. You can see that the majority of it is residing within the cortex rather than the medulla, and you'll see that only the small bit, the small loop of Henle, is actually dipping down into just the surface of the medulla, really. Then you have the other one called the juxtamedullary nephron. What does juxta mean? Juxta translates into next to. That's literally what it translates to, next to. So next to medullary nephron. And that's absolutely correct. Look at it. It's literally sitting right next to the medulla. So juxtamedullary nephron means next to the medulla. And this guy right here is quite different from the cortical nephron in the sense that it sits way closer to the medulla, and in fact, it has a really extremely long loop of Henle that penetrates the entirety of the medulla. Okay? It also has another specialized structure that's called the vasa recta. The vasa recta is another kind of capillary. Now, let me get something straight here. Remember, this blood supply of the kidney goes like this. Here's the renal artery. The renal artery will go and then branch all the way into the afferent arteriole. The afferent arteriole, I said, brings blood to the glomerulus, that tuft of capillaries right here, right? And then draining the tuft of capillaries, the glomerulus, will be the efferent arteriole. The efferent arteriole will then branch into something known as the peritubular capillaries. And this happens in both the cortical nephron and the juxtamedullary nephron. But in the juxtamedullary nephron, the peritubular capillaries will continue branching into something called the vasa recta. And this will be translated into the straight vessel. Okay? The vasa recta looks like this. It forms a hairpin loop, a characteristic hairpin loop that runs parallel to the long loop of Henle. And this will be extremely important when we talk about osmolarity in the next video. But the function of the loop of this long loop of Henle of the juxtamedullary nephron is to produce extremely concentrated urine. And the function of this long loop of Henle also is to create something called a medullary interstitial osmolarity gradient. And that's called the countercurrent multiplier mechanism. Again, we'll come across this in a later video. But the job of this vasa recta, guys, is to maintain that medullary interstitial osmotic gradient that we created. Okay? So that's the main differences. Now, how much of your nephrons are cortical nephrons? Well, in humans, 80% of your nephrons are cortical nephrons and 20% are juxtamedullary nephrons. Another specialized structure that you'll find in both of these nephrons is something called a juxtaglomerular apparatus, abbreviated JGA, and it's actually right over here and right here. So you can see it involves the distal convoluted tubule, right? The afferent arteriole, the efferent arteriole, the Bowman's capsule, and the glomerulus. And we'll take a deeper look at this next slide, all right? And when I was telling you about the collecting duct right here, right? So you can see it. Here is the collecting duct, and you can see how it has a cortical region and a medullary region. That's what I meant over here. So just to summarize, arterial blood comes in from the afferent arteriole, goes to this tuft of capillaries called the glomerulus. It'll get filtered through the Bowman's capsule, make its way through the proximal convoluted tubule, right, where it'll have the chance to go through tubular secretion and reabsorption with the peritubular capillaries surrounding it. Then that filtrate will carry on through the proximal straight tubule, down the descending loop of Henle, the ascending loop of Henle, join the distal convoluted tubule, and then finally join the collecting duct. And then after the collecting duct, it'll come down to these little minor calyces, then to the renal pelvis, then to the ureter, and so on, okay? So that's the kind of summary of this slide. Now, let's take a deeper look at this glomerulus, right? So again, here's your afferent arteriole, here's your efferent arteriole, and here's the glomerulus. But notice the glomerulus in this picture has these kind of weird like cells on top of it, okay? We're going to take a look at what these cells are. But I do want you to take a notice of something. This right here is the only time, in the body where we actually have an arteriole draining a capillary. All right? Draining a capillary. Because usually when you have a capillary, right, the arteriole is feeding that capillary. Let me do it like this. Usually the arteriole is feeding that capillary right here, and then a vein is draining it. But in this scenario, an arteriole is feeding it, and an arteriole is draining it. And in fact, this arteriole, we know, will go and branch out into a second set of capillaries. Okay, now let's take a look at exactly what all of this stuff looks like. So here again, you'll see the blood is going this way. So we know that this right here will be the afferent arteriole. And here we can see the blood going this way. So we know this structure is the efferent arteriole. These guys right here are going to be our glomerular capillaries, okay? Our glomerular capillaries. And you can see over here in pink, just like the last slide I mentioned, there is that same juxtaglomerular apparatus present, okay? The JGA again, all right? And again, you'll notice that because this right here is an arteriole, and because this guy is also an arteriole, you will find some endothelial cells and you'll find some smooth muscle cells on all of these guys, okay? Now, a specialized structure that you will find on these afferent arterioles and efferent arterioles, okay, is these purple-ish looking cells right here. And these guys are called granular cells, okay? These are called granular cells. Sometimes you might be seeing them written as JG cells or juxtaglomerular cells, okay? So these are granular cells, and they're really special because they are specialized smooth muscle cells in this area that have the ability, guys, to sense blood pressure, okay? And they also have, actually, let me say this again. So these granular cells, they basically have the ability to secrete a molecule known as renin. And this molecule renin is actually released when you have a low blood pressure in hopes of trying to bring the blood pressure back up. And it does this, renin, and if you remember, I mentioned this in the start of the video, it does this because it's an enzyme that's involved in the production of angiotensin II, okay? Now, there are specific signals that activate these granule cells to produce renin. One of them is, of course, a low blood pressure. The other one is going to be beta-1 adrenergic stimulation by the sympathetic nervous system. And the last one is going to be signals by a special kind of cell called macula densa cells. Okay, macula densa signals. And we'll take a look at this at the end of this video. But these macula densa cells, where are they located? Well, right here, if you take a look, you have the distal convoluted tubule. If you remember in the last slide, I said the juxtaglomerular apparatus involves the afferent arteriole, efferent arteriole, the Bowman's capsule, and the distal convoluted tubule, right? So right over here. This was the distal convoluted tubule right there. All I did here was just zoom in on that portion. This here in yellow are just the regular kind of distal convoluted tubule epithelial cells. But these blue cells, they have a special name. These guys are the macula densa cells. Okay? And these guys are going to be super important. Now, when we talk about the juxtaglomerular apparatus, it is actually made up of just the macula densa cells and the granular cells, okay? So remember that. Other structures that we can identify here are going to be, for example, the Bowman's capsule here. Bowman's capsule, right? Again, you can see that it's just a whole bunch of these epithelium cells, right? A whole bunch of these epithelial cells making up. This one, for example, is going to be the proximal convoluted tubule, right? This is the start of it. This one's just the Bowman's capsule. Again, these guys right here, these are your glomerular capillaries. Glomerular capillaries, okay? So, you know that one. But surrounding these glomerular capillaries, right, is going to be something very cool. These little blue cells here, which I said are these little weird like cells that are sitting on top of this capillary, these glomerulus. Those guys are going to be called podocytes. Podocytes. And these podocytes, as you can see, they have like these little finger-like projections or foot processes, if you will, that kind of surround the outer layer of these glomerular capillaries. They kind of form like a barrier, if you will, all right? And obviously, you guys should know that these glomerular capillaries are made up of only one endothelial cell layer. But something funny is that these guys are super permeable capillaries, super permeable, because they actually have holes in them, okay? And they're not like the same water-filled pores that we were talking about before. Those guys have like tight junctions in between them. These guys are just straight up large holes, large fenestrations. So this one right here is a fenestration pore, and they allow for a lot of things to just get filtered out, okay? A lot of things. If you're curious, it's about 50 to 100 nanometers in length. Another thing you'll see right past this actual endothelial layer is this blue layer here, okay? This little blue line layer. And this, guys, is just the basement membrane. It is just the basement membrane. Now, very briefly, for those of you who are curious to know, if you're not, feel free to skip this part. The basement membrane is made up of 3 parts, right? One of them is called the first one is called the lamina rara externa, and that is the side that is actually facing these endothelial cells. So this side will be called the lamina rara externa, the one that's facing the endothelial cells. There is the middle layer that is the lamina densa, and then there is the outer layer, which is called the lamina rara interna, and that's facing these actual podocytes, okay? Now, the lamina rara externa, it is just made up of a lot of heparan sulfate, which is a glycosaminoglycan, and basically it just has a lot of negative charges. And because it has a lot of negative charges, it is able to repel negatively charged proteins, okay? This will be important in a second. The lamina densa is just made up of a lot of collagen type 4 specifically, and laminins. And the lamina rara interna is made up of heparin sulfate, and again, just a whole bunch of negative charges, okay? So there's negative charges on the external side and the internal side, right? Preventing these negatively charged proteins to come in, right? Because negative repels negative. Now, why do I say that? Because you guys know that inside of our capillary or intravascular space, right, we have all these kind of formed elements, we'll call them, right? Red blood cells, white blood cells, antibodies, right, immunoglobulins. And we have these plasma proteins like albumin that are super negatively charged. And some of them might actually be able to fit through these fenestration pores. But guess what? The basement membrane being negatively charged actually repels these guys, prevents them from actually leaking out of these capillaries, all right? And keeps these guys in here. So remember, out of the things that get filtered, these guys are not one of them. None of these guys get filtered. What does get filtered? Well, small molecules, things like glucose, like urea, like amino acids, potassium, water, chloride, sodium, your vitamins, specifically the water-soluble ones, like your B vitamins or your vitamin C, okay? There's even more that I haven't mentioned, like magnesium, all these other stuff, right? All of these guys can be filtered, okay? Now, one last thing that I actually didn't mention is that these podocytes, right? Remember I said they have like these little foot-like projections? Where they're foot-like projections, they kind of come together, right? And form these little openings. And those are actually called the filtration slits. Okay, they form these things called the filtration slits with their little foot openings right here. Okay, so imagine here's one of its foots and here's another one of its foots, and in between it is going to be that filtration slit. And that filtration slit is actually about 25 to 30 nanometers in length. Okay. And, if you even want to get even more nitty gritty, there's technically like a protein that is in between the filtration slits called nephrin, and that forms something called the slit diaphragm, and that's about 7 to 9 nanometers. So like you can see, there's a whole bunch of like barriers, right? Filtration barriers that makes it so that not just everything can get filtered out into this Bowman's capsule, and only like really small molecules can come in. So far, the barriers that all of these guys that wants to get filtered have to go through will be the endothelial cell, right? The fenestration pore, then the basement membrane, then the podocyte filtration slit, and then they're inside. Okay? Cool. The last group of cells that I didn't really mention is going to be these purple cells that are just kind of studded around these areas. And these ones are called mesangial cells. And you don't really got to know too much about these. Just know that they're here. And I'll mention them once again later, but don't really focus on these too much, okay? So this is kind of the microanatomy of the glomerulus. And now that you know this, we can actually go ahead and talk about the glomerular filtration rate. Oh, and before I forget, one thing that I did not mention was that these macula densa cells here, these macula densa cells, they are located in a very specific spot because they can actually sense sodium chloride levels, okay? They are literally sensors for the concentration of sodium chloride, and you'll see why that's important by the end of the video. We'll talk about that, okay? So now, let's talk about the glomerular filtration rate and how do we actually calculate it, okay? There is a liters per day calculation, and of course there's a milliliters per minute calculation. So let's kind of go through that. Now, as I told you guys in my microcirculation, or rather the capillary filtration video, I said that we have about 7,200 liters per day of fluid going through the system, okay? We know that. Right? And we got this number by taking 5 liters per minute, multiplying it by 60 minutes, and multiplying that by 24 hours. Okay? Now, of that 7,200 liters per day, the kidney's blood flow is about 22%. Okay? So, of this, the kidney's blood flow is about 22%, which means it's getting technically about 1,500 liters per day of blood, all right? Now, 1,500 liters per day of blood, right? 60% we know that 60% of blood is plasma. So I can actually say that of this 1,500 liters per day, all right, technically 900 liters of it is actually just plasma, right? And we know that because 60% of that blood is plasma, okay? So now we know that 900 liters per day of plasma is actually coming into the glomerulus, right? So here's the glomerulus, right? You guys know here is the what? Efferent, the afferent arteriole, and then down here would be the efferent arteriole, and then here would be the peritubular capillaries. And then of course, this is the Bowman's capsule, right? This is the Bowman's capsule. Now, again, 7,200 liters per day, kidney receives 22% of the cardiac output, right? Which is 1,500 liters of blood per day. Of that 1,500 liters of blood, 60% of it is plasma, which means 900 liters of plasma per day is coming into this glomerulus. Now, of this 900 liters per day, about 20% of it will become filtered across the Bowman's capsule, which means we actually have 180 liters of fluid per day being filtered. But does that mean I'm peeing 180 liters per day? No, of course not. So what the heck is this then? Well, this fluid right here, it'll actually become reabsorbed. Okay, it'll become reabsorbed into these peritubular capillaries, and only a certain amount of it will leave. All right. Now, let's track back here. If only 20% of that 900 liters was filtered, then that means 80% of it continued onwards to the circulation, and that was about 720 liters per day. Okay, so that was the 80%. So how much of this fluid that we actually filtered, right, this 180 liters per day, how much of that is actually going to be filtered in here? Well, it's actually going to be 19.8, actually, let's keep it consistent. So 19.8% out of that 20% will be filtered again. So that basically means that 99% of this 180 liters will become reabsorbed into the peritubular capillaries, and that basically is around 178.5 liters per day. So track back. I filtered 180 liters per day into the Bowman's capsule, and of that, 178.5 liters per day got reabsorbed into the peritubular capillaries, leaving me with only approximately 1.5 liters per day for urine. Okay, so approximately, on average, based on average values, you pee around 1.5 liters per day. Okay, and that's about, this 0.8% of this percentage. Okay, so if I was to combine the amount that actually escaped filtration in the beginning plus the amount that I reabsorbed, the amount that actually goes back to circulation, guys, is 898.5 liters of plasma per day. Okay, so I came into the glomerulus with 900 liters per day of plasma, and I left with 898.5 liters per day of plasma. So that's the liters per day calculation. All right, this exact calculation, all of the things that we did, we can do it with the minute calculation. It's just a numbers change. And by the way, the title of the video is glomerular filtration. Which part do you think is the glomerular filtration here? Well, it's right here. It is the part that we actually filtered from the glomerulus, right? This is the glomerulus. This is the Bowman's capsule, right? Glomerulus, Bowman's capsule, and 900 liters per day, 20% of it is getting filtered. That's 180 liters per day. That is the glomerular filtration rate in liters per day. If you were to remember any number, I definitely say you have to remember the 20%. Okay? Now, let's do the minute calculation very quickly. We had 5 liters per minute cardiac output, right? We know the kidney is receiving 22% blood flow, which means that's around 1.1 liters of blood per minute coming into the kidney, right? Of that, we know that 60% is plasma, okay, which means about 625 milliliters per minute of plasma is making it into the glomerulus. Now, of that, we know 20%, that's the key, 20% is getting filtered, right? And that will mean that we have 125 milliliters of plasma per minute being filtered into the Bowman space. This is your glomerular filtration rate in milliliters per minute. We know that 80% escapes to the peritubular capillaries, which is about 500 milliliters per minute here. Okay, so that's that. We know that of this 125, greater than 99% of it will be reabsorbed. Okay, again, same values, 19.8%, or 99% of the fluid is getting reabsorbed, which means of this 125, 123.75 mils per minute will be reabsorbed back into the circulation. Okay, and that actually leaves me with only approximately 1.25 milliliters per minute of urine, right, per minute. Okay, and you guys know that if I were to combine the amount that escaped initially and the amount that I reabsorbed, I would end up getting 623.75 mils per minute of plasma entering back into the circulation, right? Remember, I joined with 625 and I left with 623, okay? These are the calculations that you got to know, okay? These are the calculations that you got to know. Now, here's the key question that I have for you. Why is it that the glomerular filtration rate, right, is 180 liters per day, right? And why is it that that GFR is higher than the other capillary filtrations? So if you remember in my previous video for the capillary filtration, I said that of the 7,200 liters per day, your capillaries normally filter 20 liters. But the glomerulus is a tuft of capillaries. Why are they filtering 180 liters per day? So why is it? Why is it that the GFR is higher here than other capillary filtrations? Well, that's actually a really good question. And let's go ahead and answer it. There's kind of two parts to this. So the first reason is due to the capillary structure, right? These capillaries, remember I told you, they are fenestrated. They're fenestrated. They have very large pores, okay? And because they have very large pores, more fluid can be filtered for a given hydrostatic pressure, okay? So the fenestrated capillaries is one. They literally have holes in the endothelial cells. Like that means a lot of things can get filtered. The second thing is that if you remember, in that same video, I said that some capillaries, rather than having half of the length of the capillary be filtration and the other half be reabsorption, they have filtration occurring all throughout their length. And that's what's happening with the glomerulus. So filtration occurs all throughout, occurs all length of the glomerulus, okay? And this has a reason, guys. This has a reason. If you remember, I gave the example that a high hydrostatic pressure can cause that effect. And that is exactly what we're going to talk about in the next slide, which is that in the glomerulus, we actually have a very, very high hydrostatic pressure, okay? Static pressure, which is, by the way, non-decremental, meaning it doesn't go down. It doesn't go down. So if you remember, in other capillaries, right, we would start out at 37 millimeters of mercury, and by the end of the capillary, we'd be at 17. In these guys, in the glomerulus, we start out at 55 millimeters of mercury, and we don't actually go down. We start out at 55 by the start of the capillary, and by the end of the capillary, we're still at 55. It's non-decremental. So this constant high driving pressure means that I'm going to filter a whole bunch of fluid out. That's why the filtration is higher than all the other capillaries. All right, now with that said, let's go and talk about the glomerular filtration rate. So we already know what the glomerular filtration is in milliliters per minute and in in liters per day. And obviously those values, I think they're just for men. For women, it's a little different. So for women, it's about like 160 and about 1.6 if you want to know. But the GFR is mathematically determined by two coefficients, or two variables, if you will. And let's write them like this. One of them, you guys already know, is the net filtration pressure. The other one is this Kf, which stands for the filtration coefficient. Okay, so Kf stands for filtration coefficient. Now, the net filtration pressure, again, as you guys should already know, is the sum, not sum, it is taking into account the outward pressures and the inward pressures, okay? And it is subtracting them from one another, right? So we're subtracting the outward pressures and the inward pressures. The Kf, or the filtration coefficient, it is actually being determined by two things. One of them is the capillary surface area, okay? Capillary surface area. The other one is capillary permeability. So surface area refers to how much space do I have for filtration, okay? So how many capillaries you can think of, the number of capillaries, right? Or the size of the capillary. The other one, capillary permeability, refers to the amount of pores, the amount of open fenestration pores that I have. The more fenestration pores I have, the more permeable. The less permeable. Okay, and these will all have an impact on the filtration coefficient here. Filtration coefficient. Boom. Now, I want you guys to understand the relationships between all these coefficients. So we know that the net filtration pressure multiplied by the filtration coefficient will get me the glomerular filtration rate. And I know that my net filtration pressure is outward pressures subtracted by inward pressures. What kind of outward and inward pressures? Okay, I'll tell you. So within the glomerulus, right, and this is going to be very similar with the capillary filtration video. Within the glomerulus, right, so here's the afferent arteriole, glomerulus, efferent arteriole. In blue, we have the basement membrane, and in brown are those little podocytes, right, those podocytes. Now, if you guys remember, we have a hydrostatic pressure inside of the capillary, which is just the blood pressure. That will actually be around 55 millimeters of mercury. You also have an osmotic pressure, right? The osmotic glomerular capillary pressure. GC stands for glomerular capillary. The osmotic pressure, if you guys remember, was being caused by proteins, specifically plasma proteins, mainly albumin. And over here, it's about 30 millimeters of mercury. In the Bowman's capsule, right, so BC Bowman's capsule, there is only a hydrostatic pressure. There is no osmotic pressure, okay? There is a hydrostatic pressure, and that's about 15 millimeters of mercury. And I'll tell you where that's coming from in a second. But you can clearly see that the biggest driving force right now is going to be this dude right here. The glomerular capillary hydrostatic pressure is by far the biggest driving pressure, okay? So even though there are two forces trying to push fluid out, okay? There are two forces that are trying to push fluid out, but they can't actually overpower the hydrostatic glomerular capillary pressure, okay? It's just so large for them, okay? And we can calculate this. We can calculate this with the net filtration pressure equation, guys. So here's net filtration pressure, all right? And all we had to do was just plug in the outwards, so the things that are pushing outward, right? So 55 plus, minus things that are pushing inwards. 30 millimeters of mercury for this guy, and 15 millimeters of mercury for the hydrostatic Bowman's capsule pressure. And that will be here, okay? And if you do your math right, guys, you should end up getting 10 millimeters of mercury. And if you guys remember, it's a positive number, so that means we are favoring filtration, okay? Boom. That's the net filtration pressure right there. All right, so the outward stuff is going to be the hydrostatic pressure of the glomerular capillaries, whereas the inward stuff, guys, is going to be the osmotic pressure of the glomerular capillaries plus the hydrostatic pressure of the Bowman capsule. Boom. That's that. Now, with this said, you guys understand that if this guy increases, if the hydrostatic pressure of the glomerular capillary increases, the net filtration pressure increases, and the glomerular filtration rate increases, okay? So we can say that because the hydrostatic pressure of the glomerular capillaries is basically the mean arterial pressure, we can say that the mean arterial pressure is directly proportional to your glomerular filtration rate. So if this guy increases, this guy increases. And it's based off of this pathway. Okay? Now, what else? We know that if these guys increase, obviously the net filtration goes down. We also know that if the Kf, the filtration coefficient, increases, the glomerular filtration also increases, right? Because we're multiplying. But let's talk a little bit more about the actual filtration coefficient. So, like, what actually is it? Well, again, it's based off of the capillary surface area and the capillary permeability. And what the hell does that mean? Well, let's take a look. So here we have the capillary surface area, right? Here's one capillary with a small glomerulus, and maybe it can give like this much filtration. Here we have a larger glomerulus, and you can see boom, 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 so much more filtration. So obviously, the higher the capillary surface area, the higher the filtration coefficient. Capillary permeability talks about the amount of pores, remember? So over here, I have 1 pore, 2 pore, and 3 pore. Not bad. But over here, I have so many darn pores that I'm just filtering all around the place. Look at that. So much more filtered here. So the more pores I have, the better. Now, the filtration coefficient has traditionally been thought to remain stable in physiological states and change in disease states. But, you know, recent evidence actually suggests that this can actually change both the capillary surface area and the capillary permeability. So the surface area can change by the contraction of those mesangial cells. Remember I told you about those mesangial cells? They're all over the place. If those mesangial cells contract, they're going to press on some of the glomerular capillaries and close them. And if you close them, the capillary surface area is going to go down. And they actually contract because of the sympathetic nervous system activation. Okay? The other thing is the capillary permeability. The capillary permeability has been said to change by podocyte contraction. So remember the podocytes? Remember those guys? They had like those little foot processes, right? And those foot processes formed the filtration slits, and that was one of the barriers that you actually had to get through in order to be able to filter fluid. Well, guess what? They actually have contractile ability. So when the podocytes contract, right, the podocyte contraction, it will close the filtration slits. And if you close the filtration slits, right, what happens? The number of those filtration slits goes down, okay, of slits open. And that actually means that you have a lower capillary permeability, right? So these factors have been indicated to play a role in physiologically changing the filtration coefficient, all right? So that's that. Now, to answer another question, why is the glomerular hydrostatic pressure, so this bad boy right here, why is it higher than other capillary hydrostatic pressures? So remember, other capillary hydrostatic pressures were starting at 37. But why is it that the glomerular hydrostatic pressure is starting at 55? Also, why is it not decremental like the others? Because remember, the others, at one end of the capillary was 37, the other end, it came down to 17. This guy is 55 all throughout. Why? I'll tell you why. The main reason, guys, the main reason is because if you look at it, for example, under an electron microscope, you'll actually see the afferent arteriole's diameter is bigger than the efferent arteriole, okay? And we was looking at that right here. Look at the diameter of the afferent arteriole is bigger than that of the efferent arteriole. What does this mean? Okay, quickly. The afferent arteriole, if the diameter is bigger, it can bring in a whole bunch of more blood, okay? And if the blood flow is higher, the pressure inside of this is higher. Not only that, because the actual diameter of this guy is lower, it offers a greater resistance to blood flow, trapping a whole bunch of more blood in here, meaning that it has a constant elevated pressure due to two things. One, this bigger diameter being able to bring in more flow. Two, the smaller diameter increasing resistance, keeping blood inside of this area and preventing this decremental degradation. Okay? That's why. Alrighty. The next things that we're going to talk about, and believe me, these ones are going to go super quickly, are what happens if the mean arterial pressure changes, right? What happens to the GFR if the mean arterial pressure changes, and how does vasoconstriction or vasodilation of either the afferent or the efferent arteriole change the GFR? So since we already talked about this, I'm going to go through it pretty quickly. If you have a high mean arterial pressure, guys, look at this. If you have a high mean arterial pressure, what's going to happen? You're going to increase your hydrostatic pressure of your glomerular capillaries, which will increase the net filtration pressure, which will then increase the glomerular filtration rate. Easy. If you have a low mean arterial pressure, what will happen? You will lower the hydrostatic pressure of the glomerular capillaries, which will then lower the net filtration pressure, which will then lower the glomerular filtration rate. Okay, so that's the influence of mean arterial pressure on the GFR. Now, the other thing is vasoconstriction and vasodilation. If you were to, for example, vasoconstrict the afferent arteriole, right, lower amount of blood will be able to get in here. And if low amounts of blood will get in here, right, that will actually cause the lowering of the hydrostatic pressure inside the glomerular capillaries, right? Remember, without any change to the mean arterial pressure, all I'm doing is just vasoconstricting. This will cause a lower net filtration pressure, which will lower the glomerular filtration rate. Okay? What if I were to vasodilate the afferent arteriole? Well, the opposite response would occur. I would actually bring in a whole bunch more blood. And if I bring in a whole bunch more blood, what would I do? I would increase the PGC, which would increase the NFP, and of course increase the GFR. Now, these two scenarios right here, they can be both seen in the kidneys' autoregulation mechanism that we're going to talk about in the next slide. Next thing is, what if I were to vasoconstrict or vasodilate the efferent arteriole? So right here, I am taking the efferent arteriole and I'm vasoconstricting it, meaning I have normal blood flow coming in, right? But I actually have little blood flow going out. And if I have less blood flow going out, that means more blood is actually going to accumulate in this glomerular space. And if the more blood is accumulating here, what is that doing? That is increasing the PGC, which will then increase NFP, which will then increase the glomerular filtration rate. If I was to vasodilate the efferent arteriole, the opposite thing would happen. Normal blood flow coming in, but more blood flow than usual is leaving out of the efferent arteriole, which would lower the PGC, lowering the net filtration pressure, and thus lowering the glomerular filtration rate. Now, of these two, to my knowledge and to the things I've read, only this one seems to actually occur physiologically. I've never seen this one occur. This one's more of a hypothetical situation, but it's still good for learning. This one occurs in response to angiotensin II. So angiotensin II secretion actually has receptors on this efferent arteriole, and it'll cause it to vasoconstrict. Okay, so that's what happens there. Now, finally, the last thing we're going to talk about today is, does the glomerular filtration rate always change with the varying mean arterial pressure, right? So we said the mean arterial pressure can change the GFR, but the mean arterial pressure changes a lot, like, for example, during exercise. So does that actually always change your GFR? That can't be good for the kidney. And the answer is technically no. The kidney has its own autoregulation of blood flow, which actually has two mechanisms. One is called the myogenic mechanism. The other one is the juxtaglomerular mechanism, or sometimes called the tubuloglomerular feedback mechanism. So one thing you should know is that this autoregulation is actually occurring and works in the range of 80 to 180 millimeters of mercury. And you guys remember that your regular mean arterial pressure is 93, so this covers a large basis of fluctuation. But in pathophysiological conditions, so like in disease, anything that is less than 80 or all the way to greater than 120, sorry, not 120, greater than 180, the kidneys cannot autoregulate anymore. So this autoregulation only works between 80 to 180 millimeters of mercury. Anything less than 80 or anything above 180 millimeters of mercury will mess up this autoregulation completely, okay? Now, let's go through the myogenic response first, because that's the easier one, and we've already talked about that in previous videos. So here's the afferent arterial, efferent arterial, glomerulus, Bowman's capsule, okay? Let's say you have a high mean arterial pressure. This high mean arterial pressure will increase the blood flow into the glomerulus, okay? At the same time, it will put pressure on the walls of this actual afferent arterial, stimulating these smooth muscle cells by stretching them. You guys know that when I stretch these guys, what happens? Let's take a look. When I stretch these smooth muscle cells, right, they go from a relaxed state into a contracted state. How does that happen? Well, these smooth muscle cells, they have a stretch-sensitive calcium channel, and when they become stretched, that calcium channel will open up, and calcium will start rushing into that smooth muscle cell, causing a contraction, okay? So at first, what happened? High mean arterial pressure stretches these walls, right? And very briefly increases the PGC, which increases the net filtration pressure, which increases the glomerular filtration rate. But guess what? The myogenic mechanism kicks in, and what happens then? It causes a constriction or vasoconstriction of this actual afferent arterial. Less blood flow gets in, and if less blood flow gets in, you're lowering the PGC, lowering the net filtration pressure, and thus lowering the GFR. Okay? Classic negative feedback loop and autoregulation of the kidneys' blood flow and glomerular filtration rate. Next, what if I actually had low mean arterial pressure? Well, if I have low mean arterial pressure, guys, I'm not going to be stretching the walls of my artery. And if I'm not going to be stretching the walls of my artery, what happens? Well, at the start, the low mean arterial pressure means that I have low PGC, and I have low net filtration pressure, and I have low GFR. But remember, the kidney, in order to function properly and not become damaged, needs a homeostatic glomerular filtration rate. So what it does, because I'm not stretching the walls of these guys, right, I'm not actually causing them to contract. You know what that means? If I'm not stretching them, you can kind of say that I'm going the opposite direction. I'm kind of relaxing them. And if I'm relaxing them, that means I'm going to vasodilate them. Okay? I'm going to vasodilate them. If I vasodilate them, right, what's going to happen? More blood flow than usual will come in, increasing the PGC, increasing the NFP, and increasing the glomerular filtration rate. Easy. Now, let's move on to the last thing for today, the glomerular or the juxtaglomerular feedback mechanism, or the tubuloglomerular feedback mechanism. This one is actually going to be really, really simple because we talked about it a little at the start, and it involves those macula densa cells that are sodium chloride sensors, okay? So let's take a scenario, and that scenario is this. Let's say I have a high mean arterial pressure, and this high mean arterial pressure, guys, will do what? It will come here, and it will, as we've already talked about so many times, increase the hydrostatic pressure, which will then increase the net filtration pressure, which will then increase the GFR, okay? But if I'm increasing the GFR, what am I doing? Remember I said there were those electrolytes that were getting filtered here, like sodium, like chloride, like potassium. Well, in this case, instead of saying I increase my GFR, I can say I actually increase the filtration of sodium and chloride because of this high mean arterial pressure. Now, usually, and we'll talk about this in a future video, but sodium and chloride usually get reabsorbed here in the proximal convoluted tubule, right? Here's the loop of Henle, here's the distal convoluted tubule. So they usually get reabsorbed in the proximal convoluted tubule, right? And it can show that right here. But because there's high mean arterial pressure, increasing the net filtration pressure, we're actually filtering a lot more sodium chloride than we usually do. So a lot of it will actually start leaking all the way through this tubule system until it makes its way here to the distal convoluted tubule. At the distal convoluted tubule, these macula densa cells are like, hey, wait a minute. I'm sensing a whole bunch of sodium chloride here that's not supposed to be here. So you know what they do? because they sense the sodium chloride, it stimulates them, it activates them. And in response to that, guys, they're going to secrete a molecule called adenosine, okay, which is just a breakdown product of ATP. And this adenosine, you know what it'll do? It'll come all the way back here and act on the smooth muscle cells of the afferent arteriole, and it'll cause them to contract. It'll go through vasoconstriction. If you cause the contraction of that afferent arteriole, what are you going to do? You're going to lower the mean arterial pressure. You're going to lower the PGC, lower the NFP, lower the amount of sodium chloride, right, that you're absorbing, which means less of it will actually reach these maculadenza cells, and they will actually no longer be secreting this adenosine. That's the classic negative feedback loop right there. Another thing that this adenosine can do, by the way, is come here and inhibit the release of renin by these JG cells, these juxtaglomerular cells. And if you remember, I said renin is released when the blood pressure is low. The initial stimulus was a high blood pressure. So of course, it makes sense that these guys are coming here and inhibiting these JG cells from releasing renin, from raising the blood pressure, because the blood pressure is already high. Okay, now on the flip side, let's say instead of having a high blood pressure, I start out with a low mean arterial pressure. If I have a low mean arterial pressure, you guys should already be masters of this. I will have a low hydrostatic pressure, a low net filtration pressure, and a low GFR. But again, we can actually say a low sodium chloride level. If I have a low sodium chloride level, okay, guess what, guys? Majority of it will actually get absorbed at the peritubular capillaries here, and extremely sparse levels will reach the maculadenza cells. And because very low levels of sodium chloride are actually reaching these guys, these maculadenza cells, they are going to release a what? They're going to release molecules such as prostaglandins and nitric oxide if you want. Okay, and the specific type of prostaglandin is going to be PGI2 or prostacyclin. That's another name for it. But that prostaglandin and the nitric oxide that they're going to release will come all the way over here, okay? And it'll tell the smooth muscle cells here to, hey, guys, go ahead and vasodilate for me. Okay, go ahead and relax, all right? The kidney's not getting enough blood flow. I'm not filtering enough sodium chloride, which means what? Which means you need to vasodilate here so I can increase the mean arterial pressure, increase the hydrostatic pressure of the glomerular capillaries, and increase the net filtration pressure and increase the sodium chloride, okay? That's the negative feedback loop. And again, something cool that this prostaglandins and this nitric oxide and all that stuff do, they will come here, okay? And I should put inhibit here. They will actually stimulate the activity of these JG cells to produce renin, okay? They'll tell them, hey guys, now is your time to shine. The blood pressure systemically is low. I need you to produce renin so that you can go and make angiotensin II and, start increasing the blood pressure, guys. So that's that, okay? So again, the entire point of this JG and this myogenic mechanism is to just flow auto-regulate, okay? Just regulate the amount of blood flow coming in. One of them is just the smooth muscle myogenic response, right? Where if I have too high, we stretch and we contract and we lower the blood flow. If I have too low, then I relax the smooth muscle, which brings in more blood flow, okay? Over here, the only difference is that it's just based off of the amount of sodium chloride that is being filtered. So if I filter a lot of sodium chloride, the maculadenza cells will sense that, they'll secrete adenosine, and they will constrict the actual afferent arteriole, right? Why? Because the high sodium chloride was an indicator to the maculadenza cells that, kidney's getting a lot of blood flow. That's dangerous. Let's fine tune it. If I actually have low sodium chloride due to a low mean arterial pressure, the maculadenza cells are saying, that's not a good sign. Kidney's not getting enough blood flow. Let's secrete prostaglandins and nitric oxide to vasodilate. Okay? Alrighty, guys. That's going to finish it with this video. We covered a lot today. We covered glomerular filtration, autoregulation, structure and function of the kidneys. If you guys liked the video, if you truly learned something from it, please go ahead and like the video, go ahead and subscribe, and maybe leave a comment. Thank you so much, guys. I'll see you in the next video.